Hi, everyone. So this is a good time for my talk to be because I'm also talking about a conic solver. And it's quite different, but in some ways the same. So we good? This is joint work with Leah, who's going to present after me, and she's going to look at more of an application side, where I'm going to look more at the sort of solver and algorithmic side. And Juan Pablo, who is our PhD advisor. Okay. So, what does Hypatia? Why do we call this solver Hypatia? So Hypatia was born around 400 AD. She was born in Alexandria to a fairly wealthy dude, and she became a very famous teacher. People throughout the Mediterranean knew about her. She was a famous philosopher and mathematician, and she's the first female mathematician whose life we have a pretty good record of. And there's a movie from 2009 starring Rachel Weisz about her. And Rachel wanted to make this movie because there's a very interesting story about how she was persecuted for being a smart non-Christian woman. Okay. Some of the things she did and contributed to were astronomy and also sort of the mathematics of conic sections. And so I think the main reason we called it Hypatia is because she was one of the early people to work with cones. Not in the same way that we do, but okay. So first, let me just talk about conic certificates and introduce you to conic duality. So we're going to consider a Cartesian product of primitive cones. So primitive just means that the cone is sort of irreducible. So for example, the second order cone, PSD cone, or a one-dimensional non-negative cone are all primitive. Okay. So we can write a primal-dual pair of conic problems in this way if we choose to. This is not a quadratic problem here, but at the end of the presentation, if I have time, I'll return to looking at a quadratic version of this. So we have a linear objective in the primal, some equality constraints, and this inequality constraint is an inequality with respect to our cone C. And in the dual, that inequality with Z is with respect to the dual cone C star. And the way that Hypatia is going to solve this is through the homogeneous self-dual embedding, which is used by most conic solvers these days. Okay. So I'll sort of skim over this a little bit, but that's what the homogeneous self-dual embedding looks like. It's just a sort of linear, it's a problem with no objective, and in fact, any we can take any point in these 6 variables, and let's consider that we have a solution with kappa plus tau is non-negative, is strictly positive rather. So if tau is greater than 0 and kappa is 0, then we have an optimality certificate, a primal-dual optimality certificate for our problem. And so we have a certificate of optimality and an optimal solution. In the case that tau is 0 and kappa is greater than 0, then we're going to have either a primal or dual infeasibility certificate. And these are the 2 cases here. And finally, if tau equals kappa equals 0, we actually can't make a conclusion, and it means this problem is ill-posed. I won't go into that, but there's such a thing as an ill-posed certificate that we can return. Okay, so for the algorithmic side, the way we're going to solve this is to think inside the cone. So we're going to maintain feasibility of the S and the Z, and we're going to try to work towards feasibility of the equality constraints. So cones are ubiquitous in popular culture as well. Has anyone seen this movie? I saw it when I was a kid and I loved it. All right. So first part of the algorithm is going to be setting up pre-processing our problem. In particular, removing primal and dual equalities so that we have full row rank in the primal and dual equality constraints. Okay, now we're going to find an initial iterate in those 6 variables. So we're just going to set tau equals kappa equals 1. We're going to set S and Z by taking an interior ray within the cone C, and then we're going to take the gradient of a barrier function, which I'll discuss at the end of the presentation. The negative gradient of that gives us the sort of the opposite initial part of the vector. So one thing I'll discuss later is we only need a barrier for either the primal cone or the dual cone. So this allows us to get S and Z, and from that we're then going to solve some linear equations to minimize the residuals in the linear equality constraints, and that's how we get X and Y for our initial iterate. It's not going to satisfy those equalities exactly, which means we're going to need to iterate. But we do satisfy the cone inequalities because of how we picked these points. Okay, so first we're going to calculate the residuals for those equalities in the homogeneous self-dual embedding. We're going to check our convergence conditions. So do we have an optimality certificate? Do we have an infeasibility certificate or ill-posedness? If not, then we're going to keep going. So the stepping function is where all the complexity is in this algorithm, and it's a second-order algorithm in contrast to Michael's algorithm. So we're going to solve a particular linear system which involves Hessians of these barrier functions, and we're going to solve that for affine and correction direction. So an affine direction is, I'm not going to go into the math of central path, but basically it's sort of tangent to the central path. And a correction direction is trying to bring us back towards the central path, which allows us to sort of take longer steps if we stay closer to the central path. So it's balancing this, making as much progress in sort of reducing the residuals at each iteration, but at the same time staying close to the central path so that, in future iterations, we continue to be able to make good progress. Okay. We're going to perform a line search to see how far we can move in the prediction direction. And this is going to give us, the affine alpha, that distance. We're going to use that to heuristically calculate a correction factor, which is, multiplying the correction direction that we're going to add to the prediction direction. So we get a convex combination of those two. And the further we can travel in the affine direction, it means that we're further from the, we're closer to the we're deeper in the interior of the cone, which means that we can sort of travel a long distance. It means we don't need so much of a correction in the next, in this step. Okay, finally, we're going to use the line search to step as far as possible in this combined direction. And we're going to make sure that we don't exceed a certain neighborhood parameter. So we're going to, go in the combined direction, but not too far. We're going to stay within a certain neighborhood of the central path. Okay, so the nice thing about Hypatia is it's very easy to change any part of the algorithm. So let me explain a little more. All right. The most complicated part of the algorithm was that stepper function. So in particular, we allow you to plug in any part of that. You don't have to use a combined predictor corrector. You could predict and then correct, which is what one of the canonical papers in this area does. We find the combined directions work better in practice. You can change the line searches. In fact, you don't need a line search. You could calculate, you know, what is the maximum alpha you could travel. But in practice, it's actually faster to use a line search. And most importantly, you can plug in your own linear system solver. So you can exploit as much problem structure as you want. These linear systems in the 6 variables are very structured though. So we already provide 4 different options for the linear systems. Some are sparse, some are dense, some are higher dimensional, some are very low dimensional, but they force you to use sort of dense linear algebra. Some of them require factorizations. Some of them are not factorization based, they're iterative. So in particular, one particular method we offer, it only needs a Cholesky of dimension n minus p, a dense Cholesky, to solve that linear system. The rest is just some matrix multiplications and some back solves. And if you want to use an indirect or iterative linear system solver, in fact, A and G can just be linear operators, and you only need to be able to sort of multiply by A and G and their adjoints. And so for very sparse problems or for problems with very structured matrices, you could potentially represent A and G as block matrices, with some of the blocks sparse, some dense, you know, various types of matrices that you can very rapidly apply as operators. So down the track, it might be interesting to explore how in JuMP and MOI, we might be able to preserve some of the structure of constraints. But currently, you know, vector-affine functions and whatnot are sparse representations. So you're going to necessarily lose that structure. Okay. Yeah. What? Marketing. Okay. One of the major advantages of Julia is what Stefan was talking about yesterday, genericity. So we could switch to higher precision dynamically. So let's say during the course of iterating, we seem to run into numerical issues. We could detect that. We could detect the sort of slow convergence or, you know, factorizations or failing, whatever. And we could potentially go from, you know, 32-bit floats to 64, or we could use one of the higher precision packages to go even to arbitrary floating point precision. We haven't done this yet, but maybe you could try, you know, the Hermitian semi-definite cone. There's a paper that came out just last year by some people who do a lot of work in energy and stuff with semi-definite programming, and they're like, please give us a SCP solver that does complex numbers. And it wouldn't be that difficult to extend what we have currently for that. Yeah, okay. So what different cones can we handle so far? So obviously you've seen the second order cone before. This is a PSD cone, and there's 3 dimensions. Here we have an exponential cone and a power cone with alpha is 1/4. These are ones you've heard of probably. They're in SCS, for example. But we aren't limited to these. So here are some you've probably never heard of before. So, you know, we can do epigraph of infinity norm, and it's dual the L1 norm. Obviously, you could just do this with LP, but maybe it's faster to not just use, you know, linear inequality constraints. Epigraph of the matrix spectral norm. So these n-dimensional power cone type things. Few other very useful ones, the hypergraph of the perspective of the log determinant function, and these interesting sort of sums of squares cones, which Leah's going to talk about a lot more, so I won't discuss them. So Hypatia was largely motivated by this paper that came out in 2014. And that paper, it requires only a primal barrier for each primitive cone. So you don't need a dual barrier. And there's a lot of cones for which we know efficiently computable primal barriers or dual barriers, but not the opposite. So consider you have a problem where you want sum of squares cones and dual sus cones in the primal problem. We only have a computable barrier for dual sus, which means that we can't use the Scaja and Yi algorithm. But our innovation in Hypatia is that we only need the barrier for either the primal or the dual of each primitive cone. So we're able to mix different cones for which we have primal or for some of them and dual barriers for other ones. So it allows us to be a lot more general. So the barrier functions, which you can sort of plug in yourself, the main restriction is that they have to be logarithmically homogeneous. There's also another condition called self-concordance, which gives you very strong convergence guarantees, but it's not clear that you actually need that for this algorithm to work in practice. In particular, we have experimented with various barriers which we have not proven that they're self-concordant, and probably they aren't. But it works. This is a barrier that also works until this season. Okay, so here's the meaty part. So Hypatia allows you to just define a new cone, and as long as you have a suitable barrier function. So, while there's a lot you can express with SDP and exponential cones and whatnot, MoSEC claims that you can express just about any convex problem that people care about. But sometimes you pay a high price for using those formulations. You may need to use large extended formulations, which introduce a lot of variables, a lot of constraints. And maybe you don't want to do that. Maybe you actually just want to use, say, the log determinant cone rather than the fairly large extended formulation with exponential and SDP cones. Hypatia allows you to just use the more natural sort of cones for your problem, which probably results in a much smaller dimensional problem. So the interface allows you to just create a new cone type. And you need to give it, you need to specify a barrier parameter, which is very easy to determine just experimentally. You need to specify that initial interior ray for either the primal or the dual cone. And you need a function that checks if a particular point is inside the primal or dual cone, depending on whether you have the primal or dual barrier available. And then you need to be able to calculate the gradient of the barrier and the Hessian and potentially, but not necessarily, the inverse Hessian of the barrier, which you can just get by factorization, or just their products. So pretty simple interface. Most of the cones we already have available are fewer than 100 lines of code to define them. Okay. So we have two major interfaces. One is the native interface, which is very close to that primal dual form we saw before. And it allows you to specify A and G as sort of abstract matrices or as linear operators. Or you can go through MathOptInterface for convenient modeling from JuMP or whatever. So our wrapper is going to convert MOI to a Hypatia model, optimized, and then any certificates we have, it's going to sort of bring them back and reinterpret them so we can return them through MOI. Most of the existing MOI cones already map to Hypatia cones, except for the root det cone, for which someone could try a barrier if you have any ideas. So all the CBF, so conic benchmark format is a format in which there are thousands of conic problems with second order cones, SDP cones, exponential cones stored. And using MathOpt format, we can solve those sorts of problems with Hypatia. Yeah, here's an example of a particular cone that we have defined that's not recognized in other places. And here we're using it in a constraint down there. It's pretty low level, but we plan to work on sort of maybe bringing some of these cones to MathOptInterface and working on polyJump and other JuMP extensions to make modeling with more interesting sets easier. Okay. Thank you. I do have a couple extras that I'll just skim through real quick. Here's a primal-dual form with a quadratic objective. And you can see this paper by Vandenberg on CVXOpt. They have a particular algorithm which is not based on the homogeneous self-dual embedding. So it does not detect primal-dual infeasibility. But we are planning, we have sort of a stale PR open where we want to try to implement Hypatia with quadratic objectives and without the homogeneous self-dual embedding. And because of the modularity of Hypatia, that can just be a sort of a separate module. So you could use the homogeneous self-dual embedding with a linear problem or this other sort of algorithm with a quadratic objective. And one sort of crazy idea would be to have just a general convex differentiable objective and update the Q inside the linear systems at every iteration, which would kind of give us a cone SQP algorithm. I guess the same thing could potentially work for Michael's algorithm. And it would be very interesting to compare the two. I imagine his scale's better than ours, but ours might be able to get higher numerical precision. Yeah, it'd be interesting to compare. Okay, that's all. Thank you.
So you guys have for a question? So that code that you showed us, an example code for, what is it?
Oh yeah, so that cone, well, Lee's going to talk all about him. Yeah. But I mean, one of the interesting ones is the log determinant cone. So it's now defined in MOI. But for that one, we were like, okay, this extended formulation is just too big with exponential cones and 2 SDP cones. What could we do? So we thought about, we looked at the barrier for the exponential cone, and we thought, how could we adapt that to the log determinant cone? And just by analogy, we guessed a barrier for it, and it's been working very well in practice. We don't know that it's self-concordant, but you can sort of just use analogy to guess barriers, and it seems to work. Yeah.